Saturn has been unveiled in an extraordinary new light that will fundamentally change our understanding of this gas giant. The long-awaited photographs from the James Webb Space Telescope have finally arrived, showcasing aspects of Saturn that remained hidden until now. These revelations suggest we may have overlooked crucial elements within the planet's complex ring architecture. Scientific speculation has persisted for years regarding mysterious activities occurring within Saturn's orbital bands, phenomena that could unlock profound secrets about cosmic mechanics. What groundbreaking discoveries will Webb's advanced capabilities bring to light about Saturn's enigmatic ring structure? The revolutionary James Webb Observatory has already transformed our comprehension of the primordial universe with startling imagery that challenged fundamental astrophysical principles. Now, this technological marvel is revolutionizing our perspective on familiar worlds within our own solar neighborhood. Contemporary astronomical observations are revealing planetary features previously beyond our detection capabilities. Through Webb's sophisticated lens, Saturn emerges as though it were an entirely alien world. A persistent question has captivated the scientific community. What concealed processes are unfolding within Saturn's intricate ring network? Previously, astronomers possessed only speculative theories about these phenomena, with few willing to make definitive claims about the true nature of these occurrences. Webb's mission included a comprehensive examination of Saturn, and through cutting-edge infrared detection systems combined with specialized optical filtering, astronomers achieved unparalleled observational clarity. Scientists have never before penetrated so deeply into the ring architecture or observed Saturn's surface with such precision. This enhanced observational capability is now revealing previously invisible aspects of ring formation that may resolve mysteries spanning centuries. Saturn stands not alone in appearing dramatically transformed through Webb's observations. The Space Observatory has also captured remarkable imagery of Jupiter, Uranus, and Neptune. These familiar worlds would likely be unrecognizable to casual observers. This transformation represents more than mere visual aesthetics. Webb's unique imaging approach serves specific scientific purposes. Researchers harbor strong suspicions, and these new observations are expected to provide confirmation of phenomena previously thought impossible. Beneath thick layers of cosmic debris and frozen materials, undiscovered elements may have remained concealed for eons. Speculation surrounding Saturn's unusual characteristics is far from recent. Multiple instances have suggested the presence of structures within Saturn's rings that indicate processes extending beyond conventional understanding. Saturn's ring system was historically viewed as a unified formation until space probe imagery revealed the existence of numerous distinct ring components. Current scientific understanding recognizes that these rings possess entirely different evolutionary origins and likely represent vastly different temporal periods. Certain rings are composed of particulate matter and ice, probably originating during early planetary development phases. Alternative ring formations likely resulted from accumulated rocky fragments or potentially debris from asteroidal impacts or fragmented minor planetary bodies. Saturn's ice-covered moon Enceladus has contributed significantly to ring development. This satellite produces spectacular geysers of ice and crystallized water vapor reaching heights of 10 kilometers into surrounding space, essentially sustaining one of the outer ring systems independently. These mechanisms demonstrate to researchers that Saturn's ring complex represents a self-contained cosmic ecosystem. The continuous transformations, Enceladus's active ice production, and the dramatically varied ring compositions suggest a vibrant, almost organic system that has evolved within Saturn's gravitational influence. In Webb's infrared observations, these rings manifest as luminous, dense horizontal structures with crystalline appearances that contrast sharply against the planet's dark backdrop. This luminosity results from ice and rocky particles reflecting substantial amounts of infrared radiation throughout the ring system. Saturn's appearance as a chocolate-colored orb surrounded by brilliantly illuminated rings presents a dramatically different visual perspective. Infrared filtering serves a crucial scientific function in this context. This methodology represents the only viable approach for observing internal processes within the gas giant, and researchers urgently require enhanced understanding of these internal mechanisms. Evidence may exist suggesting the presence of surface features and atmospheric conditions within Saturn's deeper atmospheric layers. During Cassini's photographic survey of Saturn, particularly its polar regions, remarkable discoveries emerged. Meteorological evidence became visible deep within the hexagonally shaped polar storm system. Some researchers described these images as resembling azure skies shining from Saturn's interior depths. While this concept challenges imagination, our knowledge of gas giant internal structure remains limited. Observations are restricted to surface gas layers and cloud formations. Similar limitations exist with Venus, where dense atmospheric conditions completely obscure interior features. Scientific confirmation of Venus's rocky composition came through remarkable probe imagery from the 1970s. Despite calculations suggesting that planets like Saturn and Jupiter consist primarily of gaseous materials throughout their interiors, these assumptions could prove incorrect, potentially revealing solid core structures. This particular image required a 20-hour exposure period of the gas giant. Webb processes multiple raw images captured through various infrared filters to create composite imagery. Saturn's new representation displays the planet as a dark sphere in warm amber and copper tones. This presentation differs substantially from familiar Hubble Space Telescope images, which typically show Saturn with distinct bright cloud bands. This difference occurs because Hubble's capabilities were limited to visible light spectrum detection and imaging. Through these new observations, scientists now perceive Saturn's upper atmospheric layers from an entirely different perspective, utilizing these images to finally understand methane absorption patterns within Saturn's environment. A fortunate circumstance aids this research because infrared radiation at specific wavelengths experiences almost complete absorption by methane gases in Saturn's atmosphere, rendering the planet dark in imagery while allowing researchers to identify precise methane gas distribution and density patterns within these dark regions. Two particular dark areas are especially prominent. Gas concentrations appear exceptionally high in these locations, providing researchers with additional information about processes occurring in the planet's deeper layers. Methane represents the third most abundant gas in Saturn's atmosphere, following hydrogen and helium. The atmospheric edge around the planet's circumference glows intensely, possibly resulting from methane fluorescence or trihydrogen ion emissions. This image was captured near the conclusion of the 7-year summer season in Saturn's northern hemisphere. Saturn's seasons extend for such lengthy periods because the planet requires approximately 29.5 Earth years to complete one solar orbit. This extended orbital cycle means each Saturnian season lasts over 7 Earth years, creating extreme and persistent climatic variations across the planet. Throughout these prolonged summer and winter periods, temperature and weather patterns can shift drastically, producing phenomena including powerful storm systems and unusual atmospheric behaviors. These extreme seasonal variations also influence the formation and modification of methane and aerosol structures within the atmosphere, which telescopes like JWST can now observe with unprecedented accuracy for the first time. These images therefore enable precise study of Saturn's meteorological processes and seasonal transformations. Surface processes and uppermost atmospheric layer activities promise new insights into deeper planetary layers. These discoveries may yield surprising revelations. Who could have anticipated that Saturn's moons would also appear dramatically different in these new observations? Webb successfully captured 3 of Saturn's 145 known satellites. Dione, Enceladus, and Tethys are visible in the imagery. Enceladus proves particularly captivating as it expels water fountains nearly 10 kilometers high from subsurface oceanic reservoirs into space. Recent phosphorus discoveries there make Enceladus a compelling candidate in the search for extraterrestrial life forms. Enceladus represents a relatively small satellite with approximately 500 kilometers diameter. It measures significantly smaller than Saturn's moon Titan, which spans 5,150 kilometers, or Jupiter's moon Europa, measuring roughly 3,121 kilometers diameter. Nevertheless, Saturn hosts numerous satellites considerably smaller than Enceladus. Some measure merely hundreds of meters across. If life truly exists on Enceladus, the potential habitat size would roughly correspond to Germany's Lower Saxony region. Dione and Tethys represent medium-sized Saturnian satellites. Dione measures approximately 1,120 kilometers diameter, making it slightly larger than Enceladus. Tethys, conversely, spans about 1,066 kilometers diameter, making it somewhat smaller than Dione, but still exceeding Enceladus's size. Both satellites are recognized for their ice-covered surfaces and intriguing geological characteristics, making them compelling exploration targets. Several upcoming NASA missions plan to visit these promising and largely unexplored celestial objects. The dramatic transformation of familiar worlds like Uranus, Neptune, and Jupiter through James Webb's filtering systems seems almost incredible. Observers unfamiliar with these planetary identities might assume Webb captured images of exotic, luminously beautiful alien solar systems. By emphasizing ring structures and specific gaseous compositions, none of these worlds resemble their appearance in countless previous images. Momentarily, it seems almost disappointing that these beautifully radiant worlds don't exist somewhere in the universe. Webb has photographed these planets across different light frequencies to unveil new details and secrets about these worlds. This new appearance alone demonstrates how limited our actual knowledge of these planets remains and how much discovery potential still exists. Uranus and Neptune possess such delicate ring systems that they remain barely detectable through other telescopic instruments. Here, Uranus's rings shine brilliantly. Professional astronomical training isn't necessary to recognize that Webb's filtering capabilities offer unique opportunities to examine these ring systems closely for the first time. The significance of this filtering extends beyond the illumination or extraordinary beauty of these images. Webb can perform more precise analytical assessments from light emissions across each individual element captured. This telescope interprets light with unprecedented sophistication. Minimal radiation levels suffice to determine gaseous compositions and detect specific elemental presence. Uranus reveals not only its fascinating ring system through infrared observation, but also completely new atmospheric perspectives and dynamic planetary processes. Infrared radiation easily penetrates dense atmospheric layers and cloud formations, revealing deeper structural elements for the first time. These images expose complex atmospheric patterns that would never be recognizable through visible light observation. For the first time, active weather monitoring becomes possible on a world millions of kilometers distant from us. Neptune also displays significantly more detail of its turbulent atmosphere through infrared observation. We can observe the planet's faint ring structures and its moon Triton with remarkable clarity for the first time. Jupiter reveals detailed atmospheric structure and massive storm systems across different light frequencies. Infrared imagery shows the Great Red Spot with unprecedented detail levels. Researchers can observe vertical structures in the images and determine temperature variations within the red spot and surrounding areas. Through this approach, Jupiter's weather patterns can now be easily monitored. This information also provides enhanced understanding of internal processes within the solar system's largest planet. Join our community now and experience every exciting new discovery firsthand.